driving a Zamboni as it's underneath, they're collecting strip after strip after strip of data. And then the SkySat's multiple different orbits. We can image the same place more than 10 times a day. When these spacecraft are working in tandem, we can do really innovative stuff. In this part of the world, tip and cue is one of the things we're interested in. So you're looking at here, image in the center and then to the right, separated by only 24 hours. This is a fast military bridge that the Russians put in as they were preparing to invade Ukraine. And then cued by these pieces of information, the sort of geointelligence that we get, and we can then point our more expensive high-resolution assets, whether they be drones or satellites, to those targets. So this extracts that imagery of troop buildup on the border over the course of several months. So even some deforestation to make room to put those troops there. These are some of the planet satellites, but they join an enormous constellation of public assets, one that's growing incredibly fast, powered by not only NASA, but the European Space Agency, various other space agencies around the world. Okay, so then what do we do with all of this measurement information? I think the next stage is discovery. And here, I love being at universities. I've been an academic my whole life before Planet. And the best part is being able to learn all of the unique insights and projects people are working on. So I want to tell you about a few that people are working on with Planet data, but I want to stress, I don't think I'm going to show you a single example that's powered only by Planet data. Every single one of these examples is leveraging pieces of data from other types of systems, including these public sensors, other commercial providers. So we operate a large university program. I'm delighted to say that TGI and St. Louis University and its partner institutions are now part of that program with data flowing into all of the institutions. We have around 16,000 users in our university program globally. And in addition, we work with several space agencies directly with NASA, with the European Space Agency, with the German Space Agency, DLR, to power additional research. And collectively, this constellation of more than 20,000 users has already generated more than 2,000 peer-reviewed scientific articles. Articles are definitely not the end of what we're trying to do here, but they are important in this discovery phase. So let's take a look at a few. One on the bottom right here, this is a guy named Dan Dixon and colleagues working on flowering trees. You can see trees flower. They do so very briefly, sometimes for only a few days. In the tropics, in particular, he's working with eucalyptus trees in southern Australia. And he's actually just left a project there using Planet data to find those flowers and go to UC Davis, a collaborative blueprint, where they're similarly looking at flowers in order to understand almond production. We have a number of different groups looking at air pollution. This one is fascinating to me because Planet satellites were not designed to study the atmosphere specifically. We prefer to look through the clouds than stare at them. But we do also see a lot of haze, and multiple investigators have taken ground station data. These are sensors for air quality, so PM 2.5 is an example, and they've fused that ground station data with Planet's high frequency, high spatial resolution imagery using machine learning techniques, and they can make maps of estimated air pollution. We've got people doing a similar thing in the water, in this case looking at water turbidity. The one on the right from an Italian university, what you're seeing there is the Venice harbor. The column on the left is typical water turbidity in Venice, and the one on the right, those three panels on the right in blue, is the dramatic reduction in water turbidity during the lockdown at the start of the pandemic. On the left side, using similar methodology, completely different group, they're studying water turbidity to understand how it affects coral reef biology and health in Hawaii. Patterns of life. I think this is something that I know that Bassett and others at TGI are really interested in looking at. And I'm quite excited by this too, because again, I'm about to show you some examples that we didn't necessarily think that Planet satellites would be perfect for. And yet, investigators are discovering this information in the data. The one on the left, Planet images at 3.7 meters resolution in those CubeSat data sets, okay? 3.7 meters. That means one pixel is as big as a pretty large F-150. And yet, these investigators were able to estimate traffic density on road surfaces, not because they can resolve every single individual car. The doves can't do that. The SkySats can't, but the doves can't do that. But because they're able to see the spectral differences between high traffic density times and low traffic density times. And so that insert there shows you, like with the water turbidity in Italy, a dramatic reduction in vehicle traffic during the lockdowns, and they've shown that for multiple different cities. Using a very similar methodology, but dealing with open markets, essentially farmers markets or pop-up markets in Kenya and Ethiopia, investigators were able to show dramatic reduction in the appearance of those food markets also during the COVID lockdowns. On the right, in Malawi, lower right, fusion of planet data with cell phone position data in order to understand cell phone usage behaviors across Malawi. The one in the top right is led by Ezra Sewell, who I believe is still at Imperial College London. And her approach was very unusual. She fused planet satellite data with Google Street View. That's a data fusion that's quite complex. It's pretty unique. What she's looking for is patterns related to wealth and poverty that are correlated with green spaces, or things like just tree density on streets. Something I heard from some of the TGI partners at Stowe University yesterday. Fusion. Okay, so a bunch of these were already fusion, but now we're looking at just direct fusion of public sensor data with commercial data sensors, including for agriculture at TGI partner University of Illinois. This is work led by the lab of Taiwan. A Belgian university in the middle is fusing planet data with Sentinel data to generate synthetic, estimated, high temporal and spatial resolution shortwave infrared data. This is a part of the spectrum that planets doves do not measure. And yet these investigators are able to build statistical models that correlate what planet does measure with these things that are measured less frequently by Sentinel. Additional example, looking at tropical forest phenology from the University of Hong Kong, and a classic now, perhaps the most cited planet paper ever, fusing planet data with Landsat and Sentinel with MODIS to make a stable, reliable, high-frequency surface reflectance product, which I'll talk about again. And now, I'm not going to go through every one of these, but I think you're starting to understand my point. Forest biomass, vegetation biomass, literally dozens of labs around the world, every single one of which is putting planet data in combination with other public sensor data sets, with field data sets, with LiDAR data sets, and they're fusing those data sources in order to generate useful products. Okay, but this is the discovery frontier, right? This is labs, postdocs, graduate students submitting papers to remote sensing environment, presenting at AGU. This is not the same thing as mitigating climate change, right? Because we need to scale those results, and then those results have to have an operational impact. So let me look at a couple of national scale examples. This is work led by Lyndon Estes at Clark University in collaboration with colleagues in Kenya and Ghana. One of the first high-resolution and high-frequency maps of agricultural systems across an entire West African country. And they were able to separate agricultural detections between the wet and dry season in order to understand the seasonal dynamics that take place in Ghana. This is a similar methodology, but working with forests, in this case in Peru. The first 1 hectare resolution, national scale, tropical biomass carbon stock map. And once this map is built, it already is, we can do spatial bookkeeping and understand how future deforestation directly causes carbon emissions into the atmosphere and actually detect which are the biggest pressures of those carbon emissions in tropical forests in Peru. If a map like this, if a tool like this is wired to a carbon offset, to a RED project like the Reduced Emissions for Deforestation and Degradation, it can begin to essentially transact with the global economy. Let's look even bigger. So we're now in collaboration. This is work really led by NASA Harvest. We're providing data to analyze changes in agricultural dynamics in Ukraine as a result of the war. And I think what is really interesting here is that the planet began its daily imaging capability in early 2017. And so, with some effort, we can not just assess what is the state of agricultural production in Ukraine today, or last week, or last month, but we can actually quantify what is the delta between Ukraine's agricultural production and activities and harvest times and turnover, cover crops between today and several years ago, okay, when the war was not taking place. We have an operational tool. This is work led by Salo Sciences, commercial company that we've been working with, taking planet data, but again, here the whole time, JEDI data from NASA, airborne LiDAR data from the state of California. They're putting those assets together in this tool, which is publicly available and open in order to understand wildfire management in the state of California. This is just California, but as a demonstration, you can imagine this tool operating across all of Australia, all of Europe. At the global scale, we have two big initiatives I wanted to highlight. One is a partnership with Norway. Airbus is also involved in this partnership, as well as KSAT. And in this case, what we're doing is releasing cloud-free mosaics of tropical forests. So with the high frequency data, we're able to put all these images together, stitch them together, and deliver these maps that really beat down the clouds. It's just probabilities. It's sort of like we could image Manaus, 30 days in a calendar month. It might be sunny in the wet season on 2 of those days, but we're going to catch those days, even if they're missed potentially by several events. And finally, a collaboration called the Allen Coral Atlas, which is work where the science part of the work is really led by Arizona State University as well as the University of Queensland. Planet is again providing data, but also we're working collaboratively to make the highest resolution map ever of the world's coral reefs. I worked on this project for quite some time, and I saw the kinds of things I'm seeing in this room today related to how we all collaborate with each other from our different backgrounds and different expertise and so forth. And it was really amazing. So, like right out of the gate, we had to take a harder look at the way Planet was generating surface reflectors products because they were behaving differently over water than over land. Because of course we were set up to do land mitigation. And what we saw was the scientists and postdocs at Arizona State and Queensland diving into the data and collaborating with our engineers. Somewhat speak the same language, but not entirely, right? And exchanging information or making this tool better. Okay, so I'm going to go all the way back to the evolution introduction with the C4 grasses and the plants and others, and talk about how we can, as a community, as a geospatial community, evolve different than those plants do, ideally quite a bit faster. Of course, we can exchange ideas laterally. One of the great ways that we're doing that is by cohering around common standards and structures in things like file types, in things like analysis environments, right, with analysis-ready data. I would I wish I could talk to Jack and the rest of you all day about this, but let's unpack fusion and sort of look at that in terms of what data types or projects or activities we've also been talking about today. So it's interesting that, like, of course, colloquially, we use the word fusion often to talk about particles and we talk about reactors. Literally, fusion is taking the particles and smashing them together and turning 2 hydrogen atoms into a helium atom. This figure has these sensor inputs that kind of look like particles. And this is not that different from what is actually happening. What we're doing is taking planet data or Sentinel data or Landsat data for all of the focus years, etc. And we're putting them in one of these common structures like STAT or an analysis-ready data structure. And we're building spatial models to get those data sets to talk to each other. This is not all that different from my conversation yesterday with professors at Aristotle University who are matching data plots in the St. Louis region. And they're looking at thermal infrared imagery. I can't recall where it's from exactly, potentially from Landsat. So now they have data sets associated with land cover types in the St. Louis area, and then they have this thermal information layer. You build a spatial model to get those 2 data sets to talk to each other, essentially. And you can go outside of the study region and make additional predictions and then go validate and stress test things. So if we look at, say, a hypothetical project where we want to make a biomass, that's, Lauren has said it already, we probably call it, this is my bias. I love making biomass maps, I can do it all day. We're getting these different input data sets, we're fusing them together to build a spatial model, and we're doing that where it's sort of wrapped around this common level 3 surface reflectance. Now, this works in the past with data, might work differently in different projects. But I want to highlight that engine where we can essentially agree as a community on what is the surface reflectance standard, right? Through something like COGS in terms of a file type, or something like stack in terms of a computing environment. And then we can generate different outputs coming out the other side. In this case, I'm interested in biomass, but next week we might be interested in a UN Sustainable Development Goal on poverty. We will probably, for the rest of our lives, argue about what the tools on the right should be, what the impact should be, what the decision makers should do with the data. We're going to do that. And that's going to be really healthy. It's going to be collaborative. It's going to be tense. We're going to argue. But if we come together on what is the community level agreement of what these standards should be, I think we're going to make a lot of progress in putting this engine together. Planet has done some of this in terms of collecting feedback from the community. So we're almost, well, we're 10 years old now. Our earliest satellites have the spectral response for those of you remote sensors in the room in row 2 there. And you can see that our initial build of our spectral response had sensitivities that were somewhat overlapping. So this means if you're a photon of light around 500 nanometers, it's sort of a coin flip if you end up with a green channel. That's not ideal. And we've since innovated, replaced all of those. They're in the process of actually being deorbited right now. And now we're operating an 8 spectral channel instrument, and we listen to the community and put that instrumentation in a way that is much more compatible with Sentinel-2 and Landsat, even more easily interoperate across the data sets. And we're going to continue to do that. I want to tell you very briefly about a couple of future missions upcoming. One is Pelican. This is a follow-on to our SkySat high-resolution constellation. So this represents a dramatic increase in our tasking high-resolution capability, sharper spatial resolution, more frequent revisits at a particular fixed point. And we're also building Tanager. We expect to launch both of these missions next year, at least the first spacecraft. Tanager is a spectrometer, a full hyperspectral instrument with over 400 channels of light. It goes from about 400 nanometers to 2,500 nanometers. And so with an instrument like this, I'm sure many of you have worked with them, are going to be able to start understanding spectral fingerprinting. Look for things like methane emissions on wellheads, or look at mineralogy in more detailed ways that we can do with our 8 spectral band instrument. So that's the picture of the next few years of the planet. Okay, so I wanted to wrap up by just saying a few things. I really, TGI is the reason, sort of the reason I'm here in terms of how we got in touch with Bassett and the rest of the team. But as I said at the top, I've been learning so much about all the different institutions and some of the motivating factors. I wanted to share I have a friend. Okay, so I said I've been working at Planet for 10 years. I had hair when I started. Seriously. And I have a friend, Sasha, who said to me one day that multidisciplinary work is the hardest work you'll ever do. Because you understand your own expertise. And you have words and names and acronyms. And I say spectral data fusion to somebody in my own domain, we know what we're talking about. And you need to work with somebody, in fact, a group of people with completely different expertise. And one of the things that requires, I think, is the curiosity, Allison said it so well, to kind of sit still and learn from your colleagues as you exchange information. This morning, when I shook hands with the NGA director, aside from terror, even just in a very brief conversation, I have the chance to learn from him some of the day-to-day realities of his job and the people that report up to him and work. I have never worked with the NGA, but I work now with literally dozens of planet employees employees who have either worked at NGA or work in close contact and close relationship with NGA. So I'm able to listen and sit and try to understand what their reality is. It's very different from my reality. I'm walking around in the jungle for a number of years in Peru trying to make these carbon maps. But we find areas where we overlap. And so I think that is the way to beat climate change. Collaborative thinking. I think we're going to do it. And I think TGI is going to be one of the flagships to do it. So I want to end there and thank everyone again for having us. Hope you enjoy the rest of your evening.
Thank you, Dr. Mascaro.